Okay, so that's case. I move on to the second algorithm, QR iterations. Okay, so it's mathematically difficult to prove the theoretical background. So I just only explain some brief or the outline of this algorithm. Okay, so basic idea comes from the any matrix, square shaped matrix A. It can be decomposed by two matrices, but Q is also normal matrix, and R is upper triangular matrix. So dense, generally, Q is a dense matrix, so dense squared matrix, and R it is the upper triangle matrix. Well, this is true, and so the uniquely, so we can decompose any square matrix. But this is not limited to the square matrix. Any shape of the matrix can decompose the Q, and also normal matrix and the upper triangular matrix. This is true. Okay, so if we have such a decomposition Q and R, we update the matrix A by computing or applying the also normal projection from right and left. But from left, so we should transpose the also normal matrix Q. Q transpose A Q. We update this matrix as the original matrix A. But now A equal QR. So substitute replace the A by the QR, and the Q is now also normal matrix. So Q transpose Q is always identity. So this is equivalent to the RQ. So this is a very interesting operation. So if you have a QR, replace the A by the RQ. QR and change the order. But RQ, it's always a symmetric or Hermitian matrix. So we update the matrix A by this new matrix as a result. But okay, so we repeat this procedure several times. This matrix, this Q transpose AQ, this converges to the diagonal matrix. It's quite difficult to explain this, why it's converged. But you can check the textbook. Yeah. Okay, so if A is a matrix, symmetric matrix, this procedure, so iterative process converges to the diagonal. So X, if you take the multiple multiple consecutive matrix multiplication by X, and then so the final diagonalize the matrix form by the capital lambda, then it is matrix A, original A is decomposed by the specific matrix, and then we have a diagonal matrix. This is eigenvalue decomposition. So if we take X as eigenvector, so this is we can go back to the definition of the eigenproblem. Yes, here we have the same formulation. So QR iteration. So we can use this procedure to solve for the sort of eigenvalue computation. So we just only need this process decompose the sort of original matrix by the sort of orthonormal and the sort of upper triangular matrix. I think as a major numerical library or the numerical software package, it already includes this process. So we can easily construct this process, solve the eigenvalue problem. Okay, so this is the QR iteration. And okay, so from here, third approach, dense linear symmetric matrix case, so parallel algorithm. But just briefly, so the image or the workflow, several step solve a huge problem on the parallel computer. So yeah, so if we solve the large eigenvalue problems in parallel, the last page, the QR iteration. Yes, these operations iteratively decompose the matrix and multiply and update the matrix. So it has the very highly the parallelism, and also apply the this algorithm and the implementation to the parallel computer system. But it is based on the iterative, iterative process and the convergence and parallel speed up. So it is difficult to expect how to say convergence ratio. So it is it includes some okay. So critical the structure of this algorithm includes very strict the sequential part. So it's avoid to accelerate by the parallel computer. So of course it shows a good convergence. It is powerful, and any matrix can be applied to this algorithm. But yeah, so if we if we apply the eigenvalue problem to the very huge and the parallel system, so we should consider to avoid the essential sequential the part from the algorithm itself. So we should introduce the more another approach. So the major numerical library. So as far as I understand, so there are 3 or 4 major libraries, but so they are taking the same approach. Inputs the dense matrix n by n. We transform the dense matrix into the very simple data format, the 3 diagonal part and the off diagonal, so 3 lines of structure. Then so we solve the eigenvalue problem for the 3 diagonal, because we have mathematically trivial algorithm solve the eigen problem for the 3 diagonal format. So we apply and then we know the very highly parallelized and optimizable algorithm. So yeah, so modern libraries. So we use the yes, good application, good implementation here. And the first step, so the converting the sort of or the dense matrix format to the tridiagonal. So it is also include sort of very highly parallel or the highly non-trivial the sequential algorithm. So yeah, we can apply the parallel algorithm here. And then back transformations, because we convert the original matrix into a specific form, so we should back transform here. So these three steps. So this is a major approach in the current or the modern numerical libraries. The first step converting the dense matrix into the tridiagonal one. So we use the Householder mirroring or the reflections of the operator. So it is defined by like this matrix. So this is just a sort of mathematical formulation. So we divide the original matrix like that. So A, 4 parts. A, so the left upper corner, so only one scalar value and the row vector and the column vector like that. And we choose the matrix like this structure, and then P as like this. So if we choose the matrix P, it's project or mirror the vector A onto this matrix. The image is like this. So if we have a vector A, this a project onto this vector. So only the first element is non-zero, so other elements are 0. So such a we choose such a operation. So just appropriately pick up the select the other vector u. We can convert convert the original matrix A into like this format. But now so just a PA, so it is only has a one element non-zero. So yeah, here like that. So recursively, we can apply this process onto the smaller. So eventually, we have a tridiagonal the format like that. So any operations here, so just multiply the vector and the dense matrix from left and right hand side. So it is very simple, and it is parallelizable. And the second step, so we should calculate the eigenvalue problem once we get the tridiagonal format. So, but I should pick show that. So yeah, here also matrix, tridiagonal matrix. It is next slide is okay. Yeah, it is easy to understand. Okay, so if we have the original large or tridiagonal the data format, so eliminating these two elements, so we can consider the similar tridiagonal formats to left upper corner, right or down corner. Also, we have similar to operation, make the matrix size the half, but also the number of the problems, sub-problems into the double number. Okay, so we have finally have such as the binary tree structure. But we need to solve these leaf programs and integrate or synthesize. No, how to say? merge the two sub-problem into the upper level problem. It also has the highly parallelism, so solving the leaf problem and also integration. So this is a very it shows a very natural high parallelism. So yeah, it is known the proposed the 1980, but from it has almost 40 years history, but still it shows a very powerful computational potential in the numerical library eigenvalue solver. Okay, so the mathematically this process is yes, intuitively understandable, but in each level we should compute this equation. Okay, so characteristic polynomial. So this can be modified like this. So just solve this equation. It's not also a simple polynomial, but also it has some it's a single pole rational equations. Okay, so once we get the lambda, so only substituting this equation, so we obtain the eigenvector. Very simple, and it has no sequential order, data dependency, just only from bottom to the upper. And the back transform is just only the reverse operation when we convert the project, the dense matrix into the three-diagonal one. Just a simple, just a different, opposite operation. Okay, so suppose just I mentioned. Oh, do you have any question? So from now, okay, yeah, go ahead.
Can you go back to slide number 23?
23. Yeah, this one?
Yeah, if we have real matrices for A.
Yep.
Is the decomposition always be a real matrix?
Oh, okay. Yeah. So here, I just limited the notation for the real matrix, but it's also applicable to the element. So in that case, element, so we should replace the transpose by the conjugate transform. Just only that. Okay. So. Okay, just a numerical chart. So I explained the whole story of the dense matrix case, but suppose it is also very big story and a big tree, symmetric and non-symmetric, and the largest and the few eigenvalue and the eigenvector pairs. And I think of the sparse case, we don't usually solve all the eigenvalue, eigenvectors pair, just only the interval or the sum or the certain number from the largest or the smallest. These are the essential case. So yeah, but the similar idea or the essential idea, it's always comes from the power method. Multiply the matrix, the initial guess, several times, and we observe whether it is converged or not. Because the theory, I showed us a very rough story. So it's not limited to the dense matrix. It is of course, sparse matrix is the target, so we can rely on the first step, so power method it is. But if we need to solve some different the situation or the configuration. So we should consider or introduce different approach to solve the sparse matrix. But okay, so sparse matrix case structure is if you understand the sort of this framework, so it is quite similar to the power iteration, power method. We just only take the several matrix, several vector to the how to say, so the searching or the vector to be treated in the sort of this iteration. Okay, so here capital V, it is a kind of the pool of the sort of the vector to be searched, and then V0 initial guess. If we iteratively multiply the sort of matrix to the sort of vector V, it is a sort of power method. But here we consider the projection, the matrix and the multiple or the vector pool. We say the subspace or subspace projection SA. So we consider this small projected matrix and solve the sort of eigenpair of this projected one. So we have the eigenpair, eigenvalue, and the eigenvector for the SA. Of course, we can convert the relation SA to the sort of original matrix A. How we have something relation SA and A. But this procedure converged sort of certain value or certain vector. So converged vector and the subspace and the value obtained the projected the eigenvalue and the eigenvectors are associated with the matrix A's eigenvalue and the eigenvector. Does it make sense? Do you understand? Okay. So, but also this, okay, so the significant part is here. So step 4, step 5. So V, so it is something or the vector sub vectors are included in the sort of a small linear space. So, but so V, capital V, and this step 4, step 3, step 4. So we have mathematically defined the sort of Rayleigh-Ritz or subspace projected matrix problem, and this is a sort of the constraint to the some minimum or approximation problem. So if we define such a cost function, you understand that this returns the scalar value, right? And it is a scalar function with such a y vector y. It is kind of normalized or constraint condition. So it's a Lagrangian. So if we use this is a Lagrangian format. So this is a minimization of this term with this constraint. So we compute some gradient of y and the sort of parameter mu, we have these two relation. If we solve the sort of two relations same times, these y and the mu, these are local optimal for the first cost function. So it means that if we choose any linear combination within the subspace V, the specific the vector it shows the sort of minimum number if we evaluate the some quadruple the format. So this is always equivalent or associated with Rayleigh's problems, projected problems. So if we compute the projected problem and then solve the eigenvalue problem, so the projected problem, so it is equivalent to the local minimum of the minimization. If we if we choose any possible subspace search, but it just return the local minimum. So if we iterate this process, always we get the same results. So we need to update the searching space or this constraint capital V different or include the different vector or eliminate the unnecessary vector from V. So we have several possible iteration to whether how we update the constraint of V. Okay, so we only introduce the truncated the matrix vector multiplication. So this is equivalent to the power method. Only so one vector, so multiply the A, always take a single vector as a searching space or the constraint. So this is a power method. And so inversion. So this is an inverse iteration. So as I explained, dense matrix, the special power method case. And so we have such series of VK. It's used in the previous iteration projection. And this is a residual. Residual defined by the AX minus V lambda. AV minus V lambda. Okay, so this is a residual, and so this is the most feasible or gradient direction is always essential direction to reduce or increase the cost function. And so we have several possibilities. So if we choose or if we design the iterative method with such the treatment of the constraint V, we can easily to understand, or we can introduce new iterative method for solving sparse linear eigenvalue problems. Okay, so one typical one is Lanchos and LOBPCG algorithm. I think the very conventional approach, or in the very classical the numerical linear algebra textbook for the sparse eigenvalue computation. So Lanchos. This is a mathematically definition and the analytic mathematical analysis. It is very strict done in the sort of very long the mathematical history. So this was a sort of very well known and powerful the numerical algorithm for the sparse eigenvalue problems. But recently, I think this one, so LBCG right hand side. So this shows a sort of much better behavior. Behavior means a sort of convergence. If we adapt appropriately, so take preconditioning, so the matrix T here, like also solving the linear system, so equation of the linear system, so it shows the good performance. Okay. What time is now?
It's 12:11, so we have till 12:20, but I don't know if you want to take some questions.
Okay, so mainly rest of my slides it is for the sort of afternoon hands-on session. So now I want to have a sort of break, but before that, if you have any question in the comments. Okay, no, okay, thank you. So we are now lunch break.